Good. So welcome back, everyone. We're essentially going to pick up where we left off on Friday. I want to continue on the topic of structure drawing and try to fill in a little more information, just do some more examples, certainly hit upon formal charge a little more. Not to mention that I've listed in your class notes what you can expect for at least the most common atoms with a formal charge of either 0 or -1 or +1. And I expect that with practice, it's not as bad as it sounds either, but I think with practice, you'll find you just internalize that. You get to the point where you see, a carbon with 3 bonds and no lone pair, well, it must have a +1 charge. Or if you see an oxygen with 3 lone pairs and 1 bond, well, it must have a -1 charge. It's just something you'll kind of get used to, I think, with practice. But if for now, at least, you wish to refer to that, please feel free. I put that in your class notes in order with the intention of it being helpful. And I've already gotten some questions on the OWL assignments, which is good. Yeah, everything seems to be going fine in that category. I also want to cover for sure the I feel unnecessarily or unreasonably difficult topic of resonance. I've been wondering for years why students come out of Gen Chem with such a minimal understanding of resonance, and I haven't come up with the reason yet. I don't know if they just don't teach it right in Gen Chem. It is a little conceptually difficult, and I'll certainly try to lead us through that today. Or it might be one of those topics that tends, with where it falls in the semester, tends to fall around late November, and everyone understandably is thinking about Thanksgiving and Christmas and final exams and having their winter break. So it might be a combination of all of the above, but I want to make sure that we come out of today's class with a clear and thorough understanding of what resonance is, because it's something we're going to run into from time to time, especially when we talk about the reactivity of aromatic compounds like benzene, which we will ultimately do. And time permitting, I would like to remind us all about hybridization in molecular shape. It's something you covered in Gen Chem, but I'm hoping at least to be able to touch on that. And if by some miracle there's even time left after that, I can always talk about alkenes a little bit. But in any case, that will leave Wednesday for us to talk about functional groups. And believe me, I can easily fill up 50 minutes on functional groups. And I don't want to go through it too fast. So, so far, the pacing seems to be working out pretty well, but I'm pretty happy with that. Good. So we started talking about structure drawing. Last time we went over another method for drawing structures that involves counting the number of valence electrons in total in the molecular species. And we did a couple of examples of species with an overall charge, but I thought I'd do a few more just to get us used to the idea of formal charge. And like I said, I don't think you'll run into, at least I hope you don't run into any charges other than -1, 0, or +1. I would say if you've drawn a structure and you discover a charge that's not one of those 3, you did something wrong. I think you'll find another way of drawing the structure that's better and gets down to formal charges of -1, 0, and +1. So we did a species like this one the other day. That guy happens to be called the Methoxide ion. Not that I really am that concerned about you memorizing that. I like to mention names of things because things do have names. And also in my experience, people are curious what things are called. But we'll get to the topic of nomenclature. I expect, could be Friday, could be sometime next week. And we'll talk more about naming compounds. But hopefully you've been practicing drawing structures. I think it makes sense to put the carbon and oxygen in the middle of the molecule, because those are the only ones that can form multiple bonds. And I think you'll find we'd better put the hydrogens around the carbon, because if we don't, then carbon won't obey the octet rule, and you'll wind up with a minus charge on carbon, actually, which it can happen. It's not common, but it does exist. But it doesn't make much sense to put the minus charge in carbon when you can put the minus charge in oxygen. And I've already given the game away. We're going to discover that that's where the minus charge is. but oxygen is way more electronegative than carbon. So I think it makes the most sense to attach the carbons to, the hydrogens to carbon, not to oxygen. And let's see, how many valence electrons do we have? 4 for carbon plus 3 more for the 3 hydrogens makes 7, plus 6 for the oxygen makes 13. And don't forget, we add 1 more for the minus charge. You add a valence electron for every minus charge and subtract 1 for every plus charge. That kind of makes sense because electrons are negatively charged. So unless I've messed something up, I think we have a total of 14 electrons to account for. Well, 8 of those are, of course, going into the bonds to carbon. That's good. We want carbon to have 4 bonds and no lone pairs, if at all possible. So carbon's obeying the octet rule. That uses 8 of our 14 electrons. That leaves 6, and they'll go as lone pairs on the oxygen. And at this point, you can do a couple things. You can observe in the material I gave you in your class notes that an oxygen atom with 1 bond and 3 lone pairs is a formal charge of -1. You can also calculate it. And I'll be honest, I have to look at the formula because I don't have it memorized. You can memorize it if you want to, but again, I believe with enough practice, non-zero formal charges will jump right out at you. And it is best practice always to label any non-zero formal charges. That's best practice. Always label any non-zero formal charges. There you'll discover that the carbon is a formal charge of 0, which we would expect. But let's see, how do you do this? It's the number of valence electrons in the free atom, which is 6 for oxygen. You subtract half the number of bonding electrons. There's 2 bonding electrons in the bond. Half of 2 is 1, 6 minus 1 is 5. And then you subtract the number of non-bonding lone pair electrons. 5 minus 6 is -1. So the oxygen is a formal charge of -1, and we expected something like that because we know the overall species has an overall charge of -1, and that's where it comes from. It's from the oxygen. And in an upcoming chapter, we'll learn that this is the conjugate base of an alcohol called methanol. And it is a species that exists. If you're thinking probably that oxygen is not real happy with the -1 charge, you would be correct. That being said, much better to put a minus charge on oxygen than on any number of other atoms. Oxygen can bear a minus charge pretty well. It's quite an electronegative element. And we covered electronegativity, at least briefly, the last time. We said that electronegativity is, you covered that in Gen Chem, the ability of an atom to suck electron density toward itself, in particular, electron density in bonds. Right, bonds don't always, in covalent bonds, the electrons aren't always shared equally. In fact, usually they're not shared equally. And so there's this tug of war on the bonding electrons. And the more electronegative atom is going to be winning that tug of war and drawing more of the electron density toward itself. And that's where bond polarity comes from. If you wanted to draw a polarity arrow pointing from the carbon to the oxygen, you can do that. That would look something like that, if you did polarity arrows like that. You might also have done delta plus and delta minus in Gen Chem, same thing. Either way, I don't care what you use, they have the same meaning. And so what that means is the oxygen's winning that tug of war on the electrons. And there are, I should also have mentioned, there are values associated with electronegativity. They were assigned by the late Linus Pauling, Nobel Prize-winning chemist. The Pauling electronegativity values are something you can easily look up. Of course, I do not expect you guys to memorize them. If ever I gave you any problems that involved Pauling electronegativity values, I would give you them. I don't expect you to memorize a bunch of numbers like that. That being said, I do expect you to know about the overall trend of electronegativity. And we said this last time, electronegativity increases from left to right on the periodic table, and it also increases up the periodic table. So the most electronegative element you're going to run into is fluorine, because we don't count the noble gases. They are not electronegative. They don't tend to form bonds. So fluorine's the most electronegative element you're going to run into. I would say probably the least electronegative element that you could run into might be cesium. I doubt we'll even run into that. Probably potassium, since we don't run into very many rubidium or cesium compounds. And anyway, they're going to be inorganic, right? They're salts. So be that as it may, that's going to be the structure of the methoxide ion. with the -1 formal charge in oxygen. What about the bisulfate ion? You know, I'm being very brave in doing this because I didn't check it ahead of time. This is going to be this is the conjugate base of sulfuric acid. So that's going to be another species with a hypervalent sulfur. Let's see if that business with the valence electrons still works. I'm feeling pretty confident. I think it will work. So we'll put the sulfur at the middle. That's the one that makes the most sense. That can form the most bonds. We want to avoid oxygen-oxygen bonds. Those really don't show up except in peroxides, and the bisulfate ion is not a peroxide. So I think it makes the most sense to put the oxygens around the sulfur in some sense. And then we have to attach the hydrogen then to one of the oxygens, just in order to minimize formal charges. And it doesn't matter which, they're all the same. And we'll learn why that is later today when we get to resonance. So put it on whichever of the 4 oxygens you want. So now let's count valence electrons. Hydrogen is 1, sulfur is 6, so we're up to 7. There's 24 more in the 4 oxygens, each of which is 6. 24 and 7 is 31, plus an electron for the minus charge makes 32. And we've used 8 of those 32 electrons. So we have 24 left to account for. And I think we'll be able to account for them on the oxygens 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. So far, so good, but I don't think that's the best structure. If you work it out, and I'll leave it to you to do that, you'll find that all 3 oxygens have the formal charge of -1, and the sulfur then has a formal charge of +2. So that's not good. So we'll make some multiple bonds in order to get rid of some of those formal charges. And you can do it with whichever 2 of the oxygens you want to. I just feel like doing it with those 2. I could just as easily have picked those 2 oxygens or those 2 oxygens. But now I think you'll find the sulfur is a formal charge of 0. And I encourage you to plug it into the equation and convince yourselves of that. And this oxygen here will have a formal charge of -1. And that's where the minus charge in the bisulfate ion comes from. But that then again, I'm getting a little ahead of myself, but that begs the question, well, why did I choose to put the minus charge in this oxygen? When I could have put it here, I could have put it here. Welcome to resonance. We're going to get to that today. And like I said, I'm going to do my level best to make sure that that's clarified to the greatest extent possible, because it's an easily misunderstood idea. So this is one of any number of equivalent correct ways to draw that structure. And it worked. So again, this is an example where sulfur has more than 8 electrons around it. I think if you count, you'll find 12 electrons around sulfur. That's allowed. We can have more than 8 electrons around any element in the 3rd row of the periodic table or below. So that's how I knew that we had to draw a structure like that, because otherwise we'd be trying to cram extra electrons around oxygen, and that's no good. Because remember, in the 2nd row of the periodic table, these elements can never, ever expand the octet. They can only have 8 electrons, never, ever any more than 8 electrons. So sulfur is going to do it this time. So I think that's one of any number of correct ways to draw the structure of the bisulfate ion. Again, that's the conjugate base of sulfuric acid. What if there's a plus charge? Well, one species you heard about in Gen Chem is the ammonium ion, NH4+. Pretty easy to tell where we should put the atoms. It makes sense to put the hydrogens around the nitrogen. The nitrogen needs to be the central atom because it's the only one that can form multiple bonds. Hydrogen can form only 1 bond, so we're not going to put the hydrogen in the middle. And then we have 5 valence electrons on the nitrogen. You just count over lithium, beryllium, boron, carbon, nitrogen, 1, 2, 3, 4, 5. And each of the hydrogens brings 1, so we're up to 9. But now we have to remember to take an electron away because we've got a plus charge. So that's how we deal with plus charges. And that leaves a total of 8 electrons. Well, that couldn't be simpler. 2, 4, 6, 8. So where's the plus charge? I think you can already tell. The one that looks funny is the nitrogen. That's going to be where the formal charge of +1 is. And we can verify that. In nitrogen, it says you start with the number of valence electrons in the free atom, which is 5. You subtract from that half the number of bonding electrons. There are 8 bonding electrons in 4 bonds. Half of 8 is 4. Oh, you can also actually state that, I've also seen that stated, minus the number of covalent bonds. It turns out to be the same thing. There's more than one way to write that formula, whichever way you want to think of it as. Again, I really do believe with practice, you won't need to bring out that equation regularly. If you want to memorize it, you can. That way, should you need it, you have it on hand. But I think after a while, you'll start to get the idea and start to recognize non-zero formal charges. Anyway, so 5 minus 4 is 1. And then we subtract the number of non-bonding lone pair electrons, which there aren't any. So 5 minus 4 is plus 1. So that shows the nitrogen is a formal charge of plus 1. And that's where the plus charge is in the ammonium ion. It's on the nitrogen atom. So that's just a little more on structure drawing, a little more on formal charges. I mean, we could spend all day doing examples, but I would like to get on to resonance and hybridization. And then we'll just touch on this business about what's called curved arrow notation or arrow pushing. Curved arrow notation is another tool like structure drawing that we use to communicate ideas in organic chemistry. We use it to show what happens when a chemical reaction occurs. Because in any chemical reaction, organic or otherwise, what you find is the movement of electrons from one atom to another, or from a bond over here to a bond over there. That's basically a thumbnail description of any reaction, whether organic or otherwise. And we're not going to use curved arrow notation a lot. It's something we use very heavily in Chem 227 and 228. So we won't do it a lot. We'll use a little bit of it occasionally. And I'll only bring it up today briefly because it always gets brought up under the topic of resonance, which in a way is exceedingly unfortunate, because what we're about to say about resonance is that movement of electrons is exactly not what is happening in resonance. But it's not just your textbook. Every organic textbook I've seen for the past 15 years always brings up arrow pushing under the topic of resonance. So that's probably yet another reason why students are easily confused by resonance. I think you have a lot of things working against you in terms of understanding resonance. So I won't talk about it much today. I'll just bring up the topic and the general rules for drawing arrows, or maybe I should say general rule, because there's like one. So it's not a very complicated topic. And we'll leave other examples of arrow pushing for later chapters. We'll use it a little bit. I won't say heavily, but we'll use it a little bit this semester, just to help us understand what's going on in certain reactions. And then, like I said, if we have a chance to go over hybridization in molecular shape, that's great. Or, I mean, I can even go over the basics just very quickly here. I will let you know the only hybridizations you're going to be caring about in this class. There's only 3, sp3, sp2, and sp. That's it. Those are the only 3 we're going to run into. We're not going to be doing any of the more exotic hybridizations like D2, sp3. We're not going to be dealing with that. You only run into those in the case of transition metal atoms in metal complexes. That's not a topic in organic chemistry. That's a topic in inorganic chemistry. So if we have a chance to do a couple of examples of hybridization in molecular shape and yield via CPR model, fantastic. But other than that, I mainly want to focus on resonance because I want to make sure we do that nice and slowly and are very clear about that. So first of all, I'm going to challenge myself to write a definition for resonance. I don't know if I can, but I will try. I will say resonance is, let me say it first before I try to write it down, because I might need a few tries to state it clearly. But I would say resonance is a phenomenon that we sometimes run into in structure drawing, where there's more than one correct way to distribute all of the valence electrons. That's really what resonance is. I'll write it down. I just wanted the chance to say it first. A phenomenon or maybe I'll say the phenomenon. Sounds a little clearer. The phenomenon of there being, that sounds terrible, absolutely terrible. Oh, well, I'll go with it. The phenomenon of there being more than one. I'm actually embarrassed, but we'll go with it. Of there being more than one. Always feel free to reword my definitions. Sometimes I do well, some cases are like this one. But feel free, it's actually a good exercise to restate definitions in your own terms, your own words. The phenomenon of there being more than one way to distribute, it's getting better, valence electrons when drawing a structure. That part of the definition I'm pretty happy with. The rest pretty much sucks, if I can say that here. And it's something you don't run into with every structure, but you do run into it. Now, a species like the ammonium ion, NH4+, this guy does not exhibit resonance. There's 8 valence electrons, and there they are. That's the only way to put them in. But a structure like, actually, the methoxide ion also does not exhibit resonance. That's the only correct way of distributing those, whatever it was, I think 14 electrons. There is no other way. If you tried, for instance, to make a multiple bond to carbon, you'd find carbon has 10 electrons around it, and that's not allowed. So that's the only way to draw that structure. I mean, of course, you can turn it whichever direction you want. That's just an equivalent structure. But that's the only correct way of assigning the locations of the valence electrons. There are no others. So the methoxide ion does not exhibit resonance. The bisulfate ion, however, does, and we've already hinted at that. We could just as easily have written the structure like this. And put the minus charge on that oxygen. And I could have written out the OH bond also. So that's another resonance form. I could also just as easily have put the minus charge on this oxygen so that it would have the 3 lone pairs in the single bond. And the double bonds would be to the other 2 oxygens, and then OH up here. So when we run into that situation, that's where we're running into a resonance situation. That phenomenon, and we'll do a few examples of this, don't worry. But that phenomenon is what we mean by resonance, when there's more than one correct way to distribute the valence electrons. We do have some rules, though. Please note that you're not allowed to turn the molecule or move any atoms. That's not fair, just turning the molecule. Oh, I found another way to draw it. No, that's not resonance. But resonance occurs when, even if you leave all of the atoms in the same relative positions, there's still at least one more way to distribute all the electrons. That's what resonance is. And I think the misunderstanding about resonance, the main one that you're going to have to guard against, and I'll have more to say on this as we get to a few more examples. The main one you need to guard against is thinking that resonance is an equilibrium. Resonance is not an equilibrium. I'll even put that down. Not an equilibrium. And you probably covered equilibrium to some degree in Gen Chem. Oh, you had equilibrium constants, and you were doing products over reactants, and you were plugging in the numbers and getting the value of the equilibrium. You loved it. I know you loved every minute. I know because I've taught Gen Chem also. We don't need to worry about that so much anymore. We're not going to get quantitative about it. But it's important to understand resonance is not an equilibrium. And I'll say this at least a few more times, don't worry. But what's going on with a species like bisulfate ion is not that it's rapidly flipping back and forth between or among these 3 structures. That is not what is going on. The truth about a species that exhibits resonance, like I said, we'll do more examples and I'll write it down as we go. But the truth about a species that exhibits resonance is that it at all times is a mixture or hybrid. You probably used the word hybrid in Gen Chem. It's a mixture or hybrid of all of those structures. No one of these, ooh, I put a carbon there, didn't I? Sorry about that. We're not allowed to just change atoms. That's a sulfur. There we go, much more better. Please make that change in your notes if you put a carbon there. You probably didn't, you probably saw what I meant. Anyway, the bisulfate ion is at all times a mixture or hybrid of those three structures. No one of these structures fully describes the bisulfate ion. The true structure of the bisulfate ion is a little bit like this, a little bit like that, and a little bit like this at all times. And don't worry, I'll write all that down. We'll do another couple of examples as well. But that's the truth. That's the truth about resonance. It's not an equilibrium. So if you remember 3 words from today's lecture, those might be the most 3 important words today. Resonance is not an equilibrium. Well, not an equilibrium is the 3 most important words. If we get that down, we're in pretty good shape. Good. So yes, and that's a little bit tricky to wrap your mind around. What it means is that when we draw the bisulfate ion, we're just going to have to pick one of these resonance forms. And that's going to be generally the case when you deal with resonance stabilized species or species that exhibit resonance. It means there's going to be multiple correct structures, and you'll just pick one. The true structure of the bisulfate ion is going to be some hybrid of these. How can you draw that? I don't know. Partial bonds? I don't really know of a good way to do that. Sometimes there are clever things you can do. I'll give you an example with benzene coming up in just a moment. But often there's no really good way to draw the hybrid. So you pick one of the resonance forms. And that's going to be the general rule when you're drawing structures and you happen to be working with a species that exhibits resonance. You just pick whichever one of the resonance forms you like. You will find it's always correct. There's always going to be a correct way to proceed in whatever problem lies before you, just by picking one of the resonance forms. And I would hope, at least the theory is, I would hope that that in OWL, if you have a problem for which the answer is a resonance stabilized species, I would hope that it would accept any of the resonance forms. If we were doing free answer exams, I would accept any of the equivalent resonance forms. Since I almost said a weird word, by the way, another common mistake is people confusing resonance and Renaissance. This is not the Renaissance era or the Renaissance fair. Resonance is a different critter. Good. Well, I want to do some more examples next. Any other questions on the bisulfate ion in particular before I disappear it? As I'm fond of saying, you mean I'm just that good? You mean I'm such a good teacher? And that was so clear that no questions are even possible. I wish, believe me, I wish that were true. I'm just teasing though, I'm teasing all of us. Good, let's do another example of resonance. We drew benzene the other day, and I'm going to use the line angle drawings. And we said, remember, of course, benzene is C6H6. There are 6 hydrogens going around the benzene ring. That's one of the resonance forms. And this is the other one. I think I forgot to draw the double-headed single arrows with the bisulfate ion, but generally that's the symbol we use to describe a species that exhibits resonance. So notice that looks different from the equilibrium arrow. This is not what we use to describe resonance. That's what we use for equilibrium. This is the symbol we use when things really are flipping back and forth. When you have starting material molecules turning into product molecules and product molecules turning back into starting materials molecules at the same time. And there's a mobile situation in which all of that's occurring at the same time, but there's some equilibrium concentration of each of these things. Again, this you will have covered in Gen Chem. And we'll probably actually do a quick review of equilibrium at some point as well in this class. But resonance is not an equilibrium. That's not what's going on here. So the true structure of benzene is at all times a mixture of those two. If you shrunk yourself down to, I'm giving you superpowers here. If you shrunk yourself down to molecular size and you stopped time and looked at a benzene molecule, you would not see this and you would not see this. I'm saying even if you stop time, you would not see those. You would see every benzene molecule at all times, even if you were to stop time, being a hybrid, a mixture of those two structures. How can you draw that? Well, with benzene, there is a cute thing you can do. I often will draw benzene rings like this. You can draw a circle in the middle. That's a common abbreviation for benzene. And in those cases where we really don't have to think about where the pi electrons are, this is perfectly fine. And if you're just drawing a structure and you want to, I'm saying with pencil and paper, and you want to draw a benzene ring, that's perfectly fine. If you don't like it, take your pick of either of those. Also perfectly fine. I have no preference for the way you do it. I will say that in OWL, the structure drawing tool that you have, I don't think it lets you draw benzene rings like this. I think you'll have to pick one of those two resonance forms, and that's fine. I'll also let you know on any of your exams, the structure drawing program that I use is somewhat similar to the structure drawing tool you have in OWL. It's a little bit more advanced than that, but it's the same type of thing. And so on exams, you will tend to see me draw benzene rings like this. When I'm just drawing structures in a lecture, I will often abbreviate the benzene ring like that. You don't have to. If you don't like that and you'd rather draw one of these structures, go right ahead. I promise I will not be offended. But every benzene molecule is at all times a hybrid of those two resonance forms. And since there's only two, and looking at those two structures, I can't see any reason why one would be any better than the other. Well, it's reasonable to conclude that the true structure of benzene is 50% like this and 50% like that. Since they're equivalent structures, I can't see any reason why one of those would be better than the other. What might it look like if they aren't equivalent and how good they are? We'll do an example of that as well, don't worry. But another way of putting it, if you'll allow me to put it this way, is if we called this resonance form blue and this resonance form yellow, the thing you need to understand about resonance is that every benzene molecule is at all times green. It's not flipping back and forth between blue and yellow. Every benzene molecule is at all times green. That is the correct understanding of resonance. And again, I hope your Gen Chem professor didn't murder it too badly, but hopefully they said something like that. Yes. Yeah, I will put out study guides with some example questions from previous exams. The idea, the question was about chapter. I mean, we're not really near an exam, so I haven't done it yet. But I will make them available on, I don't think, right? We got a lot of time. It's not till the 27th. Yeah, there's plenty of time. But yes, I've already prepared some. I have them somewhere. I don't remember where I put them, but I have them somewhere. I'll make them available. I'll also let you know, in answer to your question, there's a study guide at the end of every chapter in the textbook, and it's actually pretty good. It lists all of the topics that we cover in that chapter. Good. Other questions then? I think that's all I really need to say about benzene. Maybe we'll do one where all of them are not created equal. Next time we're going to cover functional groups. One of the functional groups we'll cover is the ketone functional group. And the simplest possible actually, this gives me a chance to do something else. I'm gonna abbreviate this structure with what were we calling that? Condensed forms of the methyl groups. By the way, if you wanted to write this instead, H3C, C double bond O, CH3, fine. Either way is fine. We have to be kind of flexible with carbon when we condense groups like this, because carbon is 4 bonds, and that makes it a little tricky to compress everything in a linear format. So we have to be a little bit flexible when it comes to condensing carbon. We are much less flexible when it comes to atoms like oxygen. For example, I'm just going to draw another condensed structure. Right now, I feel like putting the OH group of ethanol on the left-hand side of the molecule. Can you see why I wrote HO instead of OH, right? This would be weird. Right? That's no good. Because with oxygen, we can afford to be picky. Oxygen is only 2 bonds, so we can always be clear about the connectivity there. We want to be careful that we're showing the connection of the carbon to the oxygen. So with oxygen, we can afford to be picky. With carbon, we can afford to be not so picky, because carbon is 4 bonds. And so that's why I would say those two are equivalent structures. We already talked about questions of the sort, if I put X, Y, and Z on the exam, will I lose points? And again, largely for us, those questions are moot because our exams will be multiple choice. But in a case like this, the answer to that question is actually interesting, because if one were to ask that question, would I take off points for something like that? My answer is not only will I not take off points, I wouldn't even notice. I would just observe that they're the same thing and move on. So that means that you guys need to practice until you don't get tripped up by things like this. You just take it in stride, see it as another way of drawing the same thing, and move on. So there's, again, this is just another listing under, there's lots and lots and lots of correct ways to draw any given structure. Your goal is to practice until you see them all as equivalent and you don't get tripped up by things like that. And again, it takes time and practice. You know, goodness knows you're not born knowing that. I didn't expect you to come into this class knowing it. You have to practice, and I understand that. Good, so back, if I may, whichever way you wish to draw it, to this guy over here. We're gonna learn, I think already next time, that that is an example of a molecule with a ketone functional group in it. And that particular molecule happens to be called acetone. I don't think I really care if you memorize that name, but it does have a name. So there actually is another resonance form. And that looks like this. With a plus charge in carbon and a minus charge in oxygen. That is another correct way of distributing the electrons. And I'm confident if I ask you guys to guess which is the major contributor, which hybrid is the major contributor to the overall structure, I'm pretty confident in guessing that you will guess this one. And you would, of course, be absolutely right. Because in this structure, there's no formal charges. Everything is a formal charge of 0. In this structure, there are 2 atoms with formal charges. And yet, this structure does play a role in the overall description of the acetone molecule. Each acetone molecule is at all times a little bit like this. I couldn't give you a percentage. If you absolutely, rammed me against the wall and forced me to guess what percentage of the molecule is described by this, I would say maybe 3 to 5%, something like that. But this is a much better description, but it's not a complete description of the structure of acetone. But again, every acetone molecule is at all times a mixture. It's not an equilibrium. It's not flipping back and forth between those two things. Nothing is actually moving in a species that exhibits resonance. Every acetone molecule is at all times a mixture of those two structures, described better by this structure, by a large margin than by this one. But this one does matter. It's because of the presence of a little bit of this character in the overall structure of acetone that explains why acetone and other ketones do what they do in terms of their chemistry, which we will ultimately get to. We've got a chapter on ketones and aldehydes, and we'll cover what sorts of reactions they undergo. And what sorts of reactions they undergo, it probably will already not surprise you to learn, It has heavily to do with the fact that there is a partial plus charge on this carbon. It means that other species with either a partial or full minus charge are going to find that carbon atom and react with it. And that explains why ketones do what they do, because of this resonance contributor. So again, normally when we draw ketones like acetone, we'll normally draw them like this. But it's good to bear in mind that they are a little bit like this as well. So that then leaves, where are we at, 2:30? I guess I have 10 minutes. So maybe I guess I already did sort of say some things about hybridization. It would be nice if we could do a couple of examples. I'll see what I can do. I would like to spend maybe 5 minutes, I'll try to limit myself to that, on arrow pushing, because all of this brings up the very reasonable question, well, when I'm given a species that exhibits resonance, how do I find the other resonance forms? And it can be done just by inspection. It doesn't require any particular method. There's no one correct way to do it, but you can use these things called curved arrows or curved arrow notation to help you find those other forms. And as I said, curved arrow notation is used to describe the movement of electrons, which I think you already see why this is 100% bogus, because I've just been taking great pains to explain to you guys, and I think you guys have also been comprehending that in resonance, electrons moving is exactly what is not happening. But like I said, for some reason, for at least 15 years, every single organic textbook, including yours, brings up arrow pushing in the context of resonance. So I feel I wouldn't be doing my job well if I didn't at least bring up the idea. Let's go back to our friend, the bisulfate ion. We said that that's one of the resonance forms. And we got also this one. Remember, we're not allowed to move any atoms. We have to keep all of the atoms in the same relative positions, no turning the molecule. We're just looking for different ways of distributing all of the electrons. That's another one. And what's the last one? I guess we have our oxygen with the minus charge down here. That's the third one. But by the way, it might have occurred to you, what if we put the double bond between, or we put a double bond between sulfur and the OH oxygen? Can you do that? Answer is yes. You'll find then that this oxygen is a formal charge of +1. I would encourage you to verify that for yourselves. And you'll have instead 2 oxygens with a -1 charge. So the overall charge will still be -1. It'll be +1 and the 2 -1. So you get an overall charge of -1. And as you would guess, that's a very minor contributor. I don't think we even, these 3 are by far the most important contributors to the overall picture of that molecule. So what if we were given this structure and we wanted to make our way to this one? How would you do that? Well, we would look at what the changes are. It looks to me like we've gone from 6 electrons around this oxygen to only 4. So clearly we've used 2 of these 6 electrons to form another bond between sulfur and oxygen. And we can do that by showing movement of electrons with a curved arrow. When you're drawing curved arrows, they can have any of a variety of shapes. Anything reasonably pleasant looking is fine. You can have the arrow make whatever kind of shape you like, but there's only one rule that you need to know for arrow pushing. It always is that the electron pair starts at the tail of the arrow and the electron pair always ends at the head of the arrow. Always, always, always. There are no exceptions. That's the only rule you need to worry about. So we've just said that we've taken one of these 3 lone pairs and stuck it in between the sulfur and the oxygen to make another bond. And you can show that any number of ways. I'm going to start my arrow here at that lone pair and show the arrow ending in between the oxygen and sulfur. I could just as easily have done one underneath, showing this lone pair instead. It's the same thing, perfectly acceptable. But we can't stop there, because now even sulfur is going to have too many electrons around it. So if we now compare the structures again, it looks to me like we've lost a bond here in between that sulfur and that oxygen. Those two electrons in that bond have gone onto this oxygen atom, giving it a plus charge. We went from 2 lone pairs to 3 lone pairs. So we'll just draw an arrow starting at that bond and ending in the vicinity of that oxygen atom. I could just as easily have drawn it on the other side of the molecule. Anything round and about the vicinity of that oxygen. I would say show some restraint. Don't go woo and draw it way up here. You know, just end it around and about the vicinity of that atom. And that's fine. And so we can use these arrows to help us find this other structure. Likewise, if we then want to get from this structure to this structure, looks to me like I'm putting an electron pair back in between that oxygen and the sulfur, and then I'm also breaking one of those sulfur-oxygen bonds. I'm putting that electron pair that used to be in a bond onto that oxygen atom. We go from 2 lone pairs to 3 lone pairs. So that would be one of any number of correct ways of showing that process that is not a process. You see how ridiculous this is, and you see why I'm so dead set against using arrow notation, or rather introducing arrow notation in the context of resonance, because arrow notation is used to show movement of electrons, and we've just taken great pains to show movement of electrons is exactly not what's happening. But I figured I needed to say something. It's in your book, just like it's in every book. So I needed to say something. I would say this whole business with electron pushing is optional. If you find you're able to find other resonance forms without using it, great. It's not mandatory to use it. But it's a tool that you can use if you want to help yourself see other resonance forms. I still have 2 minutes, so let me show you a wrong way to draw the arrows. This is a very common question that I will get at this point. Let me redraw these 2 structures. So as long as you remember resonance is not an equilibrium, we're in good shape. Whoops. There we go. A lot of lone pairs on this thing. Good. So a question I will frequently get here, and we'll end with this, is why can't I just go like that? It's a very common mistake to make here. And it looks fine at first. But I think if you carefully draw what you get after doing that, you'll see the problem. You don't get this. What you get instead is this. And here we've got an oxygen with 10 electrons around it. That's bad, right? Oxygen cannot expand the octet. And over here, we only have 6 electrons around that oxygen. So that's why it's wrong to do it that way. That leaves us, I think, in a pretty good place. Certainly touch base on those 3 hybridizations, sp3, sp2, and sp, and the shapes that go with them. They're the only ones you'll need this term. Other than that, have a great day, and we'll pick up there on Wednesday.